Hello, and thank you for watching this presentation. My name is Wheaton Schroeder. I'm a sixth-year PhD student at the University of Nebraska-Lincoln, studying under Dr. Rajiv Saha. And today I would like to talk about our new approach to dynamic flux balance analysis, or dFBA. Our approach is called the Optimization and Explicit Runge-Kutta based approach to performing dFBA. We're nicknaming our approach ORKA. dFBA is an optimization-based tool which can be applied to a genome scale model to study the time evolution of metabolism. Currently, there are two approaches to dFBA, but they are either limited in stability, accuracy, and/or tractability. In order to address these issues, we've created the optimization and explicit Runge-Kutta based approach and applied it to a multi-tissue model of Arabidopsis to show its utility. This work is published in scientific reports with an associated GitHub repository. We began by reconstructing core metabolic models of 4 representative tissues of Arabidopsis thaliana: the leaf, the stem, the seed, and the root. The model statistics can be found in this image shown in box 2, as well as some of the important exchanges that happen across the system boundary. When these 4 tissues were linked together, we call this the Path 773 model because it represents 773 different genes in the Arabidopsis genome. Once the Path 773 model was created, we set about creating the ORKA formulation. While the mathematics are too cumbersome to show here in a poster presentation, we did include the pseudocode from which you can implement ORKA on the left-hand side of box 3, as well as a workflow diagram sort of in the center, which will show the logic of how we implemented ORKA. One thing I would particularly like to note about the ORKA method, which we developed, is that we can substitute in several different kinds of Runge-Kutta methods. While there are a few caveats, this would allow us to tune the numerical accuracy, stability, and tractability of any system to which we apply the ORKA method. Once the ORKA was created, we then applied it to the Path 773 model, specifically looking to take this model all the way from germination to silique ripening and the beginning of the senescence phase of the Arabidopsis life cycle. So shown here in this image is the 7 different life cycle stages that we considered when building our model and how this influenced the in silico representation of the plants. As a result of applying ORKA to the Path 773 model, we were able to produce a significantly more complex and accurate Arabidopsis model than was produced even 2 years ago by including 2 extra tissue types, 5 extra growth stages, and about 30 more days of growth. When we did build our model, we fixed whole plant behavior and instead studied reaction level and concentration level implications of that whole plant behavior. So what we were able to do is study the flow of metabolites and the flow of reactions. This resulted in us coming up with the hypothesis that pools of metabolite are kept by the plants to facilitate transportation. In summary, we've created the ORKA approach to dFBA and applied it to a multi-tissue model of Arabidopsis thaliana. We're hoping to sophisticate the ORKA approach in future to use it as a tool to make absolute metabolite concentration estimates and hopefully use this data in future to predict enzyme kinetics, both applied to Arabidopsis and to other organisms. That is the end of my presentation. I'd like to thank you for taking the time to watch this, and if you have any questions, please feel free to contact me.